Welcome to Lab 1, in which we will be exploring the application of Newton's second law to one-dimensional and constant motion. There are several concepts within physics as a whole that will be covered within this lab. For example, Newton's first law, which states that an object at rest will stay at rest, or an object at motion will stay at motion, unless acted on by an external force. In addition to this, we also use Newton's second law, which establishes a relationship between force, mass, and acceleration in the equation force is equal to mass times acceleration. In addition to this, we will use velocity and the velocity update formula and position and the position update formula in order to calculate displacement and compare the computer model to a real-life situation. Motion is a concept with several components that can make it difficult to track and study. However, it can be simplified. The purpose of this lab is to do so by studying an object that is traveling in a single direction at a constant velocity. I began by making observations by rolling a tennis ball across a table and used Tracker to follow its motion. I then uploaded the data to Excel for later comparison. Using my first 2 points from the Tracker data, I was able to calculate a constant velocity of 0.82 meters per second in the negative x-hat direction that I would be able to use for my computational model. I extrapolated this to a final time of t equals 0.534, which is the length of my observed motion in my real-life Tracker model. I set the ball's initial position at the origin and used Newton's second law to find its subsequent position as the time period delta t had passed. However, because the net force was equal to 0, the final velocity equaled the initial velocity for each iteration of the velocity update formula, and therefore motion was constant. After putting the data from the computer model into Excel, I was able to compare it to the data from Tracker. It's evident that the computer model was able to maintain a constant slope of negative 0.82 throughout the graph. This is because exterior forces were removed from the virtual environment. Therefore, the virtual ball would have rolled into perpetuity. As for the Tracker model, it was able to closely follow the computer model at the beginning. However, even a ball is not resistant to external forces such as friction. For this reason, the ball began to slow down and it would eventually come to a stop. Possible changes to the experiment that would make the lab more accurate include changing my ball to include one with less bumps that would decrease the force of friction acting on it. In addition, I could also change the surface in order to also reduce the force of friction. There were several assumptions and decisions made throughout the lab that made it unique. These assumptions and decisions could present potential questions to be asked about the experiment. For example, what if the axes were flipped? As stated earlier, the ball was moving in the negative x-hat direction. This is because the ball was moving from right to left on the screen. However, if the ball was moving from left to right, I would likely have chosen it to move in the positive x-hat direction on my graph. This would have changed the graph that compared the computational model to the observation model. However, it does not inherently change the results of the lab. Regardless of it moving from left to right or right to left, observed motion was supposed to be constant, especially in the computational graph. If it moved in the positive x-hat direction as opposed to the negative x-hat direction, external forces such as friction would have still acted on it, and it would have skewed the results to not perfectly match the computational model. Additional curiosity can be derived from the fact that we state that F net is equal to 0 as opposed to F is equal to 0. This is because F net is comprised of multiple forces that tend to cancel each other out. However, it is impossible to pull these forces apart. There are so many different forces, and without additional information, we cannot name all of them. For example, there's the air resistance force, there is force from friction, there is also gravity and the normal force, all acting within the system. In addition to these forces, there are many others that we cannot even begin to name without more information about the system. In conclusion, Lab 1 introduced a simple experiment that would allow us to see possible errors and miscalculations that could occur within future, more complicated labs. In addition, the lab introduced us to concepts such as Newton's first and second law, in addition to velocity, displacement, and forces. We were able to see intended forces act on our system, in addition to unintended ones that we must account for in future labs.